Have you ever pondered the intricate dance of communication that takes place within our brains? How do neurons, the fundamental units of the nervous system, manage to pass on messages so efficiently and accurately? Today, we're going to delve deep into this fascinating process. Imagine a neuron at rest. It's sitting there, minding its own business, with a negative charge on the inside compared to the outside. This is due to an unequal distribution of ions, primarily potassium and sodium, across the cell membrane. This state of equilibrium, known as the resting potential, is carefully maintained by clever little ion channels and pumps. Suddenly, a stimulus comes along and triggers the neuron. This opens up ion channels and allows a flood of sodium ions into the cell. With this sudden influx, the inside of the cell becomes less negative, a process known as depolarization. Now, if this depolarization reaches a certain level, something interesting happens. It triggers the opening of voltage-gated sodium channels. This causes a rapid influx of even more sodium ions, further depolarizing the cell. This influx of sodium ions leads to a positive charge inside the cell. This creates what's known as the action potential, a rapid spike in electrical potential. It's like the cell suddenly shouting out a message. But this state doesn't last long. After reaching its peak, the sodium channels close and voltage-gated potassium channels open up. This allows potassium ions to leave the cell, restoring the negative charge inside and repolarizing the cell. In some cases, the membrane potential briefly becomes even more negative than the resting potential before returning to its resting state. This is called hyperpolarization. This whole series of events, from resting potential to hyperpolarization, is what allows the action potential to propagate along the neuron, facilitating communication between cells. It's a beautiful, coordinated dance of ions and electrical charges, all happening in fractions of a second. To recap, the communication process within a neuron involves a sequence of steps. Starting from the resting potential, a stimulus triggers depolarization. If depolarization reaches a certain threshold, it triggers an influx of sodium ions and the creation of an action potential. This is then followed by repolarization and, in some cases, hyperpolarization. These steps allow the action potential to propagate along the neuron, providing the basis for cellular communication. This complex ballet of ions is happening right now, inside your brain, enabling you to understand these words. It's a testament to the intricate and finely tuned processes that underpin life as we know it. So, next time you learn something new or experience a sudden insight, spare a thought for the humble neuron and its